Hello everyone, and welcome to this theory recording on capacitor and inductor circuits. So this part of the recording will be focused mainly on the capacitor. We're going to be describing what the capacitor is and some of the important equations that govern the performance of a capacitor. So what is a capacitor? A capacitor is a passive element that stores energy in its electric field. Capacitors usually comprise of two plates that are separated by an insulator, which is known as a dielectric. So as you can see in this figure, you've got your two plates, which are typically two metal plates, and those two plates are separated by a dielectric which will have a certain permittivity. The symbol for a capacitor would be C. The circuit symbol is indicated on the right hand side. That's the one that you see there. And in terms of polarity, there are certain capacitors that will have polarity and some that don't. So the diagrams below show first the polyester capacitor, secondly the ceramic capacitor. Both of these capacitors don't have polarity, meaning you can connect them in whichever direction. And then you have the electrolytic capacitor, which is C, which is the one that would then have polarity, meaning there is a certain type of connection that you look at. Typically with the electrolytic capacitors, you'd look at the capacitor with the longer leg, and that would be the positive terminal, and the one with the shorter leg would be the negative terminal. The unit for capacitance is farads, and an equation that characterizes the capacitance as a function of the physical parameters of the capacitor itself is given. C is equals to eta A over D, where the first variable is your permittivity, and then this is your cross-sectional area, and D would be the distance between the plates. There are many factors related to the capacitor that are proportional to the voltage drop across the plates of the capacitor, which we'll see in the equations that we will be deriving. It's important to remember the following. When you think of a capacitor, think voltage. Now, some important equations to remember. Number one, the current flowing through the capacitor is given by IC as a function of time is C dV dt, or I is equals to C dV dt. This equation indicates to us an important quality related to the capacitor, and that it is not, or rather which is that it is not a linear element, right? We can see that the current is the capacitance times the derivative of the voltage with respect to time. Second, the charge across the capacitor, or across the plates of the capacitor, Q is equals to CV. Notice that the V's are highlighted in red just to show the dependence of capacitors and the voltage across the plates of the capacitor. Third, the voltage across the plates of the capacitor. So we would take equation 1 and we would make V the subject of the formula. So we integrate both sides. And what we then find is that the voltage is going to be given by 1 over C integral from t0 to t, I dt plus the voltage at time t is equals to 0, which is your constant integration. Number 4, the energy stored in the capacitor, omega C is equals to a half CV squared. Again, the dependence on voltage. Number 5, the behavior of the capacitor under DC conditions. So how do you deal with a capacitor under DC conditions? For us to know this, first we need to determine what the resistance of a capacitor would be, or rather the impedance of the capacitor under these particular conditions. So what is the typical equation for the impedance of a capacitor? That would be given by minus J over omega C. Now, DC conditions would imply that the frequency tends to 0. So it's a very, very small number which tends to 0. And if the frequency tends to 0, what that tells us then is that the denominator is very small, meaning this whole value of ZC would tend to infinity. And in electrical terms, that would become an open circuit. So under DC conditions, constant voltage source or the constant current source of whatever value, the capacitor will become an open circuit. And finally, when looking at your series and parallel connections, so your series connection of capacitors, determining your equivalent capacitance would be a similar equation with if you had a parallel combination of resistors. So 1 over CQ equals 1 over C1 plus 1 over C2 all the way to 1 over Cn. And when you have a parallel combination of the capacitors, the equivalent resistance is as if you would have had a series combination of resistors. So C equivalent is C1 plus C2 plus all the way to Cn. Thank you for watching this video and enjoy the course.